let's visually go over integrable gradient flows. This is based on a paper by Bloch, Brockett, and Reishu. The paper's central discovery is a simple equation that unifies two different dynamics. It shows how a matrix L evolves over time through a double interaction with a fixed matrix N. The equation describes a system moving downhill, or more accurately, uphill, on an energy landscape. The solution L, T, evolves in the direction that most rapidly increases a value defined by L and N, eventually settling at a maximum. The paper's discovery is that the equations for the Toda lattice Flaschke form equations from classical mechanics, and the gradient flow of the function on the isospectral set of L are identical. By making the specific choices for L, tridiagonal, and N, diagonal, for the Toda system, it turns out that the matrix Ln is precisely the matrix B from the Flaschke form. Therefore, the Toda lattice's evolution is not just a Hamiltonian, energy-conserving flow, but is also a gradient flow. It is always moving in the direction of steepest ascent on its landscape, which is why it naturally flows to a stable equilibrium, the peak, sorting the eigenvalues onto the diagonal. The mathematics describes a projection. The full isospectral set of matrices, a high-dimensional curved manifold, is projected down onto a flat, convex shape, the polytope. The gradient flow happens on the manifold, but we can visualize its shadow in the polytope. This chart, from the paper, shows the shadow of the flow within the polytope. The vertices represent sorted eigenvalues, and the lines show different starting configurations, all flowing to the stable equilibrium. We can imagine the gradient flow as rolling uphill on an energy surface. The peak of the hill is the stable equilibrium point. This interactive 3D plot shows trajectories on a conceptual energy landscape. What does this flow actually do? It sorts the eigenvalues of the initial matrix L, 0. The system evolves until L, T, becomes a diagonal matrix, and the final ordering of the eigenvalues on the diagonal is determined by the entries of N. For the standard Toda lattice, this corresponds to sorting the eigenvalues in increasing order. The double bracket flow is a continuous dynamical system that solves the symmetric eigenvalue problem. For an advanced tutorial on how to apply this, and more tutorials, check out the GitHub link in the description.